All right, so let's talk about some subcortical structures. So when we say subcortical, we mean those structures deeper within the brain. So subcortical beneath the cortex. And let's go way beneath the cortex to the brainstem. So the brainstem is that piece of tissue that connects your brain up top with your spinal cord down here, that would be down here below. So whereas the spinal cord is more or less just a bundle of afferent and efferent nerves, the brainstem has some very important structures. So to start out with, the brainstem is divided into three different portions. They are the midbrain, which is most top. So this would be the midbrain right here. And then there is the part that has the bulge on it, and that is the pons. And then beneath the pons, there is the medulla. And then beneath the medulla, there is the spinal cord. So I would draw that down here. So the midbrain, pons, and the medulla. What I want you to know about the pons is that you can see that it has this thing right here is connected to it, and that is the cerebellum. So the pons is the part of your central nervous system that connects the cerebellum, which is very important for movement, to the rest of your nervous system. Also know that within the pons, there is a series of structures that we call the reticular formation or the reticular activation formation. And this is the part of your brain that regulates your sleep and wake cycle. It's the part of your brain that regulates your level of arousal, meaning your level of consciousness. So if someone has damage to the brainstem, they're probably going to have damage to the reticular formation at the pons. And if they do, they're going to have trouble having the appropriate level of consciousness. And this would be someone in a vegetative state or in a coma. So the medulla is the most inferior portion of the brainstem. Some people even think of the medulla more as the top part of the spinal cord rather than the bottom part of the brainstem. A lot of motor fibers that are coursing from your brain down to your body cross at the medulla. So you guys probably know that the right side of your brain controls the left side of your body, and the left side of your brain controls the right side of your body. That's true. But at some point, that signal has to get from the right side of my brain, which is on the right side of my body. It has to get over to my hand, which is moving, which is on the left side of my body. That crossing of those motor pathways happens at the medulla. And that is what is referred to here when this says descending pyramidal motor fibers decussate. So we use the word decussate in this context to mean that they cross from one side to the other. So the brainstem provides a lot of autonomic, life-sustaining functions. So the signal that is being sent to your body, telling it to breathe beneath the level of your awareness, that's generated at the brainstem. The signal that is being sent to your heart from your central nervous system, telling it to beat, that's coming from your brainstem. Your sense of thirst and your sense of hunger to keep everything in balance within the body, and everything, thinking back to high school, there's the word homeostasis, which means that all your cells have what they need, they're getting all the oxygen and the nutrients, and they're able to get rid of all the waste, everything is in balance. Homeostasis. So the brainstem is responsible for maintaining the homeostasis of your body. Other subcortical structures that we're going to talk about are the basal ganglia and the cerebellum. Now, there's tons of subcortical structures. I could spend a couple of semesters talking about them, but we only need to focus on the ones that are important to us as speech therapists. So I'm going to introduce the idea of the basal ganglia and the cerebellum, and we're going to come back to these two structures again and again throughout your education, just like we will be coming back to the brainstem again and again. So the basal ganglia. So there's a group of structures deep within the brain that are called the basal ganglia. You have a right basal ganglia, a right basal ganglion, and a left basal ganglion. Plural, it's basal ganglia. And I'm going to talk about the basal ganglia as a singular structure or a paired structure. You have a right and a left. But the basal ganglia is really two sets, paired sets of smaller structures. The caudate nucleus, the putamen, and the globus pallidus are three of the structures of the basal ganglia. You don't need to know that. We're not going to get into it, but I want you to carry it with you that the basal ganglia is a group of structures. It's not one thing, although we will talk about it functionally as one thing. The basal ganglia works in your body to regulate your muscle tone, which is the tightness of your muscles. You don't want your muscles to be too tight. You don't want them to be too loose. The basal ganglia regulates that. The basal ganglia also regulates your posture and your postural adjustments. So as I'm sitting here talking, I'm really focused on the words that are coming out of my mouth. I'm not really focused on keeping the muscles of my back contracted to keep my body upright. I'm not thinking about that. But my basal ganglia is generating that signal beneath my level of awareness so that I can have appropriate posture to complete this volitional task of speaking to the computer. The basal ganglia also plays a role in allowing you to initiate motor movement and learn new motor movement. And the basal ganglia also plays a role in taking extra involuntary movements that might be in your motor plans. Here's a coronal slice that shows you some of the structures we're talking about and how deep they are within the brain. So someone with non-functional basal ganglia, if these are the things that the basal ganglia does normally, then if your basal ganglia is not working appropriately, you're going to have abnormal muscle tone. You can have abnormal posture, inappropriate posture. You're going to have difficulty learning new motor skills. Like, don't expect to be picking up the piano or a new sport if you have basal ganglia problems, because you're going to have a lot of difficulty with new motor learning. People with damage to the basal ganglia or a non-functional basal ganglia have difficulty initiating motor movement. They know the movement they want to initiate. They know the movement they want to produce. They just can't get their body to initiate it, or it's more difficult for their body to initiate. And also, these individuals may have excess involuntary movements in their body. What I've described to you is the profile of someone with Parkinson's disease. And Parkinson's disease is sort of the touchstone example of what we think of when we think of basal ganglia dysfunction. And as a speech therapist, we spend a lot of time working with people with Parkinson's disease, so we're going to be coming back to this. All right, the next subcortical, the last subcortical structure we're going to talk about, I believe, nope, almost, is the cerebellum. And it is this highlighted little piece of your brain back here that, as we've already said, is attached to the pons, and it's under the occipital lobes. The cerebellum is responsible for fine-tuning and coordinating our movements, monitoring our movements, and making sure there are not any errors in our movements. Errors in tone of muscle, range of movement, force of movement. So as you're doing something motorically, the cerebellum is getting a signal from the brain telling it what the goal is. And the cerebellum is getting the actual raw motor plan. And the cerebellum is monitoring these two things and making sure that the motor plan is going to successfully achieve the goal. So if I'm going to reach for my bottle of water, the closer my hand gets to the bottle of water, the more careful I have to be. Let's say the bottle of water is open, sitting on my laptop. I'm reaching for it. Now, the closer my hand gets, the higher the stakes become. The higher the stakes become, the more exact my muscle movement has to be. The more exact my muscle movement has to be, the more my cerebellum is engaged in making sure that I am not going to screw this up, that I'm not going to knock over that water bottle, that I'm not going to overshoot and have an error and spill water on my laptop. The best way I can explain the function of the cerebellum is to explain to you that when an individual drinks alcohol, the first thing that gets hit, and hit hard, is the function of the cerebellum. And this is also why people that are drinking alcohol often spill their cup over. That's because normally their hand would zero in on it successfully, but because the cerebellum has turned off, their hand shoots past it and knocks it over. So the more coordinated movement needs to be, the more the cerebellum is involved. So speech is a highly coordinated and fast movement. It involves hundreds of muscles in your body, tons of body structures that all have to come and dance together for the appropriate production of speech. And it's the cerebellum that comes into play and allows you to produce this articulatory dance that is speech without any errors. At the top of the brainstem is a structure that is known as the thalamus. The thalamus is known as the relay station for sensory information coming into the brain. So all this sensory information coming from your eyes, coming from your ears, coming from your skin and your bones, all that sensory information, all the wires carrying that sensory information are going to pass up through the thalamus. And the thalamus is going to act like a relay station and it's going to be sure that the body sensation gets sent up to the parietal lobe, that the visual sensation gets sent back to the occipital lobe, and that auditory sensation gets sent to the temporal lobes. Although your sense of smell does not pass through the thalamus. There are a lot of other types of cells that support the neuron, but we're just going to talk about the neuron. The neuron is the cells in the CNS and the PNS that transmit electrical signals. The part of the neuron that receives electrical signal from another neuron is the dendrite. The dendrites receive an electrical impulse from another neuron and then transmit that electrical impulse to the cell body or the soma of the neuron. And if that neuron decides that it is going to pass that electrical signal on, then the electrical signal is sent down along the axon, which is this long projection that comes off of the cell body. And the axon of that neuron is going to attach to the dendrites of other neurons. And in this way, the central nervous system is a web of billions and billions of connections between neurons. Some neurons are only efferent. They're only motor. Their function is to transmit motor plans from the brain down to the body. We only have a few 100,000 of these. We only have a few 100,000 of these, which is not a lot comparatively. The other side of that coin is the afferent neurons, the sensory neurons. These are the neurons that provide the pathway between the sensory receptors in our body up to our central nervous system, up to our brain. We have about 5 million sensory neurons, which is still not a lot. Compared to once you get to the brain, if you look at the brain, all the little neurons that have all the connections in between them, these are the interneurons. They're not transmitting sensory information across large areas of the body. They're not transmitting motor information across large areas of the body. They're just there talking to the neuron right next to them. We have billions, perhaps even trillions of interneurons. And it's the interneurons where our high-level processing of information really occurs. The neurons that are really responsible for transmitting impulses over large areas of our body, like the afferent pathways that are transmitting sensory information from my hand up to my brain, or the neurons that are responsible for transmitting motor information from my brain to my hand, these neurons have a coating on them of a white fatty substance that is referred to as myelin. And myelin allows an electrical impulse to be transmitted along the neuron at approximately 100 meters per second. And myelin serves to insulate the neuron as the same way that we have rubber that insulates the copper wires on all our devices. So the reason, this is the power cord to my laptop. It's a little frayed. There's a little bare wire right there. The reason I don't really spend a lot of time sticking my finger into this part of my laptop wire that is frayed. That's because I'm afraid I'm going to get shocked. In other words, I want this electrical signal to go from the wall through this wire to my laptop. I want it to go from point A to point B. And if I cut the rubber and put my finger in there, there's a good chance that a lot of that electricity is not going to make it to the laptop because it's going to be redirected into my body. And that's what I don't want to happen. But if it does happen, then my laptop's not going to be getting the electrical signal that it really needs. So myelin is there to allow our myelinated neurons to transmit electrical signals as efficiently as possible. Not all neurons are myelinated. Only the ones that are responsible for transmitting information across large areas of the body are myelinated, meaning our afferent and our efferent neurons. The cortex is not myelinated. It doesn't have, those neurons up there, they don't have to, they're not thinking about transmitting electrical signals over large areas of the body. They're just thinking about talking to the neurons right next to them. So they don't have to be myelinated. And it's the myelin that makes white matter white, and it is the lack of myelin that makes gray matter gray. So if you look at this image here, you see this gray area up here. That's the cortex. That's the gray matter that's not myelinated because it's not sending information anywhere. It's just processing information. But you see all this white stripes. Those are white matter pathways that are responsible for sending electrical signals across large distances.